Imagine, a test tube lies in the red desert, a titanium cylinder the length of an index finger sealed in absolute sterility. Inside is a handful of Martian rock, perhaps the first proof that we are not alone in the universe, but no one will ever be able to retrieve this evidence. This is not science fiction, this is the reality of January 2026. 33 test tubes are lying on the surface of Mars right now. One of them contained something that silenced an entire hall of scientists on 10th of September 2025. Something that the reviewers of Nature magazine could not find an explanation for, except for one, the most incredible one. And this test tube may remain there forever. On the 18th of February 2021, a 6-wheeled vehicle weighing 1 ton broke through the Martian atmosphere at a speed of 20,000 kilometers per hour. 7 minutes of controlled descent. The heat shield heated up to 1,300 degrees, a parachute with a diameter the size of a basketball court. And finally, 8 rocket engines lowered the Mars rover on nylon cables into a cloud of dust. The landing site was chosen 15 years ago. Crater Reservoir is an ancient bowl with a diameter of 45 kilometers on the edge of the Asida Plain. 3.5 billion years ago there was a lake here. Rivers carried water across the western edge of the crater, forming a delta, a fan of sedimentary rocks in which the oldest traces of life on Earth are found. Ken Farley, the mission's principal investigator from the California Institute of Technology, would later explain the logic behind the choice. Orbital images showed a delta, irrefutable evidence that a large lake once existed here. A lake is a potentially habitable environment, and the delta's rocks perfectly preserve traces of ancient life in the form of fossils. The Mars rover was named Perseverance. The name turned out to be prophetic. For 3 years, the device methodically traversed the crater floor collecting samples of volcanic rock. These were interesting finds, important for geology, but not the reason for the mission. The real goal lay ahead, in the sedimentary layers of the ancient delta. At the beginning of the summer of 2024, Perseverance entered the Neretva Valley, a 400-meter wide riverbed that once flowed into Lake Jezero. On both banks stood the rocky outcrops of the Svetli Angel Formation, clay and siltstone compressed by time into stone. On Earth, such rocks are ideal preservers of organic matter. On the 18th of July 2024, the rover's cameras captured an unusually shaped rock. It was a triangular fragment measuring 1 meter by 60 centimeters, partially buried in a dry riverbed. The team named it Chayava Falls, after the waterfall in the Grand Canyon. At first glance, nothing special, a reddish rock among thousands of other reddish rocks. But when Perseverance moved closer and pointed its instruments at the surface, the routine ended. There were stains on the stone, small black dots which scientists have named poppy seeds, and larger structures, light in the center with a dark halo around the edges. These have been dubbed leopard spots. Such patterns on Earth usually mean one of two things, either chemical reactions involving microorganisms or processes that create conditions for life. Joel Hurwitz, a planetary scientist at Stony Brook University and deputy principal investigator for the Pixel instrument, recalled that they immediately realized they had stumbled upon something truly interesting and exciting. On 21st July, Perseverance drilled a rock core from Chayava Falls and sealed it in a titanium tube. The sample was named Sapphire Canyon. No one knew then that this test tube would change everything. To understand exactly what Perseverance discovered, we need to descend to the molecular level. The rover carries 23 cameras and 7 scientific instruments on board, but 2 of them played a key role in the story of Chayava Falls. The first is PXL, an X-ray lithochemical analyzer. It can determine the elemental composition of rock with the precision of a grain of salt. The second is Sherlock, a deep ultraviolet spectrometer. Its task is to search for organic molecules and determine the mineral composition. When Pixel directed an X-ray beam at the leopard spots, the data turned out to be strange. The dark halos contained iron and phosphorus in an unusual combination, most likely the mineral vivianite. The light centers were saturated with iron sulfides, presumably greigite. This in itself is interesting. But what really intrigued the scientists was something else. The spatial distribution of these minerals indicated redox reactions, chemical processes in which some substances give up electrons and others accept them. On Earth, Such reactions in sedimentary rocks are almost always associated with life. Microbes use organic matter as a source of energy, reducing sulfates and oxidizing iron. A byproduct of their metabolism is precisely these mineral associations. Phosphates and iron sulfides grouped around points where bacterial colonies once existed. Then Sherlock spoke up. Ultraviolet light revealed complex aromatic organic compounds in the rock. Not just carbon, but molecules with a ring structure characteristic of biological systems. Joel Hurwitz called this data a smoking gun, irrefutable evidence of the presence of organic matter in ancient mud. Organic matter on Mars is nothing new. It has been found there before, but context is everything. Here, organic molecules were found not just in rock, but in rock with leopard spots, in a sedimentary layer that formed at the bottom of an ancient lake, in a mineral matrix that serves as a hallmark of microbial activity on Earth. 3 lines of evidence converged at a single point. Characteristic texture, indicator minerals and organic carbon. The mission's scientific team spent a year trying to find an alternative explanation. Abiotic processes, chemistry without life, are also capable of creating similar structures. Volcanic activity, meteorite impacts, the interaction of water with rock. Each hypothesis was tested, modelled, and compared with the data. When the reviewers at Nature magazine completed their independent assessment, the verdict was cautious but unprecedented. No convincing evidence of the abiotic origin of these structures had been found. This did not mean that life on Mars had been proven, but it did mean something almost as important. For the first time in history, scientists could not confidently rule out a biological explanation. On the cold scale, a system for assessing the reliability of extraterrestrial life detection, the discovery received a rating of 3 out of 7. Signal from a potentially habitable environment, no contamination from Earth, requires sample delivery for final conclusion. The keywords here are sample delivery. On the 10th of September 2025, journalists gathered at NASA headquarters. The press conference had been announced a week earlier, but the topic had not been disclosed. Rumours were circulating in the scientific community. Acting NASA Administrator Sean Duffy was the first to speak to the press. His words were reported by news agencies around the world within an hour. After a year of testing, the reviewers came back and said, "We can't find any other explanation. This may well be the clearest sign of life we've ever found on Mars." She was followed by Katie Stack Morgan, Scientific Director of the Perseverance Project at the Jet Propulsion Laboratory. She chose her words with surgical precision. Astrobiological claims, especially those related to the potential discovery of past extraterrestrial life, require extraordinary evidence. Publication in a peer-reviewed journal is a critical step because it guarantees the rigor, reliability, and significance of the results. Joel Hurwitz presented the details, slides with images of leopard spots, spectral analysis graphs, mineralogical maps. He explained chemistry as if he were telling a detective story, and in essence, that's what it was. The combination of chemical compounds we found in the Bright Angel Formation could have served as a rich source of energy for microbial metabolism. But the mere fact that we saw all these compelling chemical signatures did not necessarily mean that we were looking at a potential biosignature. We needed to analyse what this data could mean. A year of work, dozens of specialists, hundreds of model runs, and a conclusion that fits into a single sentence. Abiotic explanations are less likely, but we cannot completely rule them out. Translated from scientific to human language, we may have found traces of ancient Martian life. To know for sure, we need to bring a sample back to Earth. The article was published on the same day in Nature magazine under the title Redox Mineral and Organic Associations in the Jezero Crater Mars. 122 authors, data from 4 instruments, 1 year of peer review. The global media ran headlines about possible life on Mars. The scientific community reacted more cautiously, but even skeptics acknowledged that this was the most convincing evidence we had ever had. The test tube containing the Sapphire Canyon sample was stored in the rover's storage compartment. 30 grams of rock that could revolutionize our understanding of the universe. All that remained was to pick her up. And here the story takes a breathtaking turn. The Mars Sample Return Program was conceived as the crowning achievement of planetary science. 3 decades of preparation, a joint project between NASA and the European Space Agency. the most complex engineering challenge in the history of robotics. The plan was as follows. Perseverance collects samples and leaves some of the tubes on the surface as a backup. At the end of the 2020s, a landing module with a small European-made rover will be sent to Mars. The rover will collect the tubes and deliver them to the landing platform. There, a rocket, the first in history to launch from the surface of another planet, would take the container into orbit. A European orbital vehicle would intercept it and send it to Earth, landing in the Utah desert. Total time, more than 10 years. Cost, according to initial estimates, about $7 billion. But estimates tend to increase. By 2024, an independent audit showed that the actual cost of the program would reach $11 billion. The deadline was pushed back beyond 2040. The US Congress demanded explanations. NASA feverishly redesigned the mission architecture in an attempt to reduce the price. By January 2025, the agency had presented an updated plan worth $7 billion, but trust had already been undermined. And then came May 2025. The White House administration published a draft budget for the 2026 financial year. The figures looked like a death sentence. Total funding for NASA was proposed to be cut by 24%. The science budget was to be slashed by almost half. And Mars sample return was on the list of programs to be completely eliminated. The wording was ruthless. The program had significantly exceeded its budget, and its objectives will be achieved by manned missions to Mars. The document did not specify when these manned missions would take place. The scientific community reacted immediately. Victoria Hamilton, chair of the Mars Exploration Program Analysis Group, MEPAG, and a planetary scientist at the Southwest Research Institute, did not hide her disappointment. When memoranda are issued stating that we want to be the dominant power in space, the question arises, how can we leave something so ambitious behind? Two 10-year reviews, authoritative reports by the National Academy of Sciences that set the priorities for space research for the next 10 years, identified the return of Martian samples as the main task for planetary science. Now this task hangs in limbo. Congress disagreed with the White House. By January 2026, lawmakers had passed a compromise budget, $24.4 billion for NASA, nearly $6 billion more than the administration had proposed. Scientific programs retained their funding, but Mars sample return was not included in this budget. The program, on which billions had already been spent, was officially terminated. The European rover assembler, almost ready for testing, was left without a mission. Engineers who had spent years working on a rocket to launch from Mars received notices of transfer to other projects, and 33 test tubes remained lying in the Red Desert, 400 million kilometers from the nearest laboratory, capable of answering the question, is there life in them? Lindsay Hayes, senior research scientist for Mars exploration at NASA, said at a press conference in September, "We hope that these samples will eventually be brought back to Earth, where they can be studied in ground-based laboratories." The word hope hung in the air. Scientists warned of another problem: time. Organic molecules do not last forever, even in sealed test tubes. Cosmic radiation slowly destroys complex compounds. With each passing year, the chances of obtaining a definitive answer diminish. Perseverance's plutonium power source is designed to last for approximately 10 more years. This means there is a strict deadline. If a mission capable of picking up the tubes does not arrive during this time, the rover will not be able to deliver them to the collection point. Ken Farley put it bluntly, "If construction does not begin within the next 2 years, I do not believe it will ever happen." But the history of space exploration has one consistent pattern. When one door closes, someone is bound to open another. On 22nd July 2025, a month and a half before publication in Nature, a very different kind of press conference was held in Beijing. Hu Zhenqian, academician of the Chinese Academy of Sciences and chief scientific director of the Tianwen-3 mission, presented details of a project that could change the balance of power in planetary science. China intends to send 2 spacecraft to Mars in 2028. The landing module will collect at least 500 grams of soil, 15 times more than the entire Perseverance collection. The orbital spacecraft will deliver the samples to Earth by 2031. No intermediary rover, no docking in Mars orbit requiring precision engineering. One mission, from launch to landing. The technology is impressive. Instead of a wheeled rover, There is a drone capable of collecting samples within a radius of several hundred meters from the landing module, a drill that will penetrate to a depth of 2 meters, a first in the history of Mars exploration. For comparison, Perseverance collects cores about 5 millimeters deep. The main scientific objective is to search for traces of life. Hu Zhenqian outlined 3 priorities: searching for potential signs of life on Mars, including biomarkers, fossils and archaea, studying the evolution of the planet's habitability, and researching its geological structure and history. He emphasized that the mission is open to international cooperation, from the development of instruments to the joint analysis of samples. The irony is clear. While American lawmakers were arguing about budgets, China was methodically building a spacecraft that could be the first to reach Mars. But here's what's important to understand. From a scientific point of view, it doesn't matter whose flag's on the rocket. If Tianwen-3 succeeds, the samples will be sent to laboratories. International teams will have access to the material. The question of life on Mars, a question that humanity has been asking itself for thousands of years, will finally be answered based on direct evidence. Not on remote measurements, not on interpretations of spectra, on physical samples that can be cut, heated, irradiated, and studied under an electron microscope. The US Congress understands this too. In the same budget that buried Mars sample return, there is a line item for $110 million for the Mars Missions of the Future program. The goal is to develop technologies that will be useful for both robots and manned expeditions. This is not a replacement for a full-fledged sample return mission, but it is an acknowledgement that the story is not over. Perhaps Perseverance's samples will eventually make it to Earth, aboard a commercial spacecraft or as part of an international consortium, or through some scheme that has yet to be invented. Perhaps the Chinese drone will find something even more convincing at a completely different point on Mars. Perhaps in 20 years an astronaut in a spacesuit will personally pick up a titanium tube of red dust. We don't know, but we know otherwise. 400 million kilometers away from us, at the bottom of an ancient lake that dried up before the first multicellular organisms appeared on Earth, lies a stone with leopard spots. Inside it is a chemical signature that we cannot explain by anything other than life, and cannot confirm by anything other than direct analysis. That's not an answer, it's a question, the most important one we've ever asked. And he waits.